Okay, so that is a common base stage. It's recognized because, as such, because the input signal goes to the emitter and the output comes out of the collector. All right, so we can see what happens here in terms of amplification. Suppose this input changes by some delta V. The emitter goes up by delta V. So let's think about this very carefully. If the emitter goes up by delta V while the base is fixed, what happens to the current? The current decreases, right? Because the base emitter collapses. So the current collapses. So this current drops by a factor of delta V. So we say IC drops by an amount equal to GM delta V. Remember the definition of transconductance, right? It said if the base emitter voltage changes by some amount, the collector changes by GM times that amount. And the current drops by GM delta V because the base emitter voltage has shrunk in the scenario. If this current decreases, what happens to this voltage? The voltage goes up. So we say V out rises by GM delta V times RC. So that tells us that the voltage gain of the common base stage is given by GM times RC, and it has a positive sign, unlike the case of the common emitter stage. In the case of the common emitter stage, when the base went up, the collector came down. Here, they both go in the same direction. Okay, so that is the scenario that we have for the common base stage. We also would like to find the input resistance of the circuit. So the input resistance is obtained by sitting here and looking into the emitter. And we know from 115A that Rin is equal to 1 over GM. By the way, again here we are assuming that the early voltage is infinite. So the input impedance of a common base stage is relatively low because 1 over GM is relatively low resistance. If the current is if the bias current is 1 milliamp, 1 over GM is about 26 ohms, so it's a pretty low resistance. So there are some applications in which we would like to have a low input resistance for our circuit. In those applications, we might use a common base stage. Okay, and finally the output resistance. If I sit here and look, what do I see? So R out is equal to what? So again, looking down, we don't see anything. We see infinity because the early effect is infinite. The output resistance of the device is infinite. So all that's left over is RC, so that would be RC. So these are the basic properties of the common base stage. Okay, what's interesting to note is that the input resistance of the common base stage with this condition is independent of RC, right? So remember that. It's independent of RC. So even if RC goes towards 0, if it becomes a short circuit, this resistance is still 1 over GM, right? It's independent of RC. And that brings us to the next problem. So for the next problem, number 4, we have the following. So we want to find gain and input, output resistances of this circuit. So I have a common emitter stage like so. V in, V out, RC. Okay, but this collector is connected to a transistor like this. So we call this Q1, we call this Q2. And we'd like to find the voltage gain of the circuit. All right? Okay, the voltage gain and the input and output resistances. All right, moving on to the next amplifier stage in bipolar technology, namely the emitter follower. So let's change the color to maybe orange. So I'm going to talk about the emitter follower. All right, so the emitter follower, in its simplest case, consists of a single transistor biased by means of an ideal current source. So we call this ideal, and we have an input here and an output here. And the collector, as usual, goes to VCC. So the way we identify the circuit is by observing that the input signal goes to the base, the output comes out of the emitter. And let's assume for now that the early effect is negligible. So then what can I say? How much is the voltage gain from here to here? Well, let's just play with it a little bit. Like before, we apply a little voltage step here, delta V, and we ask ourselves, what happens to the output? Okay. Well, one observation comes to our aid here. This current is constant, right? If the current through a bipolar transistor is constant, what can we say about this base emitter voltage? Assuming this. The base emitter voltage has to be constant, right? So say IC is equal to IS x of VBE over VT. If the collector is constant, because it's forced upon the transistor by this current source, then the base emitter voltage is constant. That means that this base emitter voltage is always constant. All right, so this is, for example, 800 millivolts below this under all conditions, as long as we are in the forward active region. So if the base voltage goes up by delta V, what should happen to the emitter? It should also go up by delta V because the difference between these two has to be constant. So this also goes up by delta V. So the voltage gain of a circuit in the ideal case is 1, right? And that's how we can justify it. Of course, you could draw the small signal model and prove it, but you can see even just from basic observations that the voltage gain has to be 1. Okay. In reality, this current source may not be ideal, or it might be replaced by a resistor. So here's a more realistic situation of the emitter follower, V in and V out. So there is some resistance here, RE. This might be a physical resistance, or it might simply represent the output resistance of this current source if it's not ideal. So we know the voltage gain of the circuit from 115A. So we say AV is equal to RE, which is the resistance from emitter to AC ground, divided by RE plus 1 over GM. You might recognize this as this. So they have the same denominator. Even though here the output is at the collector, here the output is at the emitter. Okay? How about the input resistance? The input resistance of the emitter follower, if we have an RE here, is equal to R pi plus beta plus 1 times RE, which is the same as that circuit. So it should be, right? Because the input resistance here is independent of RC, right? So if RC goes to 0, this circuit reduces to that circuit. And that's why the input resistances are the same. Okay? And then how about the output resistance? If I sit here and measure the output resistance, how much do I see? I see RE to ground, but then I see something else looking at the emitter of the transistor, and these go in parallel. So I have RE in parallel with, what do we see if we look into the emitter of a transistor while its base is at AC ground? It's 1 over GM, provided that the early voltage is infinite. So that's 1 over GM. Okay, so those were what we found in 115A for the emitter follower. Okay, so that completes our bipolar analysis. This brings us to problem number 5. So repeat these results if VA is less than infinity. So we want to find the voltage gain, the input resistance, and the output resistance of this circuit if the transistor has a finite RO here, which goes from the collector to the emitter. All right, that's problem number 5 for homework number 1. All right, that completes our bipolar studies. Now we're going to go to MOS studies. Okay, let's add one more page here. One more. Okay, we go back to page 4. All right. So we say MOSFETs. All right, so we saw that a MOSFET consists of a piece of silicon on which we have created 2 N plus regions, for example. So these are highly doped N-type material. And they're sitting on what we call a substrate, and that substrate is P-type. P substrate. And then over here we grow a thin layer of oxide. This is an insulator, so it cannot conduct. And then we have this conductive material, which we call the gate. So this could be, for example, this is conductive. It could be metal. It could be some other material. This is oxide. So it's non-conductive. Non-conductive. All right? Okay. So what I have drawn here is an NMOS device. So we call this an NMOS device, N-type MOS. And we call this terminal, which is sitting on top of the oxide, the gate of the device. So we connect a wire here. We call that the gate. And then these two, which are symmetric, we call one of them source, the other one the drain. So this is the source. This is the drain. How do we distinguish between the source and the drain? So we say the source is the one with lower potential. Okay, so that's how we, for an NMOS device, the terminal that is at lower potential is called the source. The terminal that is at higher potential is called the drain. And of course, that's unique. That's the gate. All right? And our symbol for the NMOS device looks like this. This is the gate. This is the source. This is the drain. All right? Okay. So that's what we have. And we decided that this device can operate as a voltage-dependent current source under certain conditions. So we constructed this circuit here. We connected a fixed voltage to the gate. We call this VGS, gate source. Then we connect the voltage source from the drain to ground. We call that a VDS, drain to source. We actually made this variable. So we made that variable, and so that's VDS. And then we monitored the drain current of the device. The drain current is the conventional current, meaning positive current, flowing from the drain to the source. So in the NMOS device, actually what's happening is that the electrons start from the source and go to the drain. They go from lower potential to higher potential, but the conventional current is related to positive direction of current flow. So the current is going this way, from the drain to the source. Okay, so we said that this gate source voltage has to be large enough to turn the transistor on. And that means that we would like to create a channel here consisting of electrons. So we have some electrons here. And for that to happen, this voltage has to be greater than the threshold of the device. So we pick VGS to be greater than VTH. This is so that to turn on the device. Okay, if the device is off, it's not particularly useful, so we have to at least turn it on. Okay, so now that we have a channel, we begin to change this voltage by means of this voltage source and measure that current. And this is what we observe. ID as a function of VDS. So this voltage is greater than a threshold, is fixed, and we're just sweeping this voltage. So what we see is that there's a region in which this current is constant. In this region, the device acts like a current source because its current is constant. But then if the drain voltage falls too much, the device no longer acts as a current source. So this region is called the saturation region. And it's unfortunate that we have this name here for the MOS device, which is has a very different meaning than saturation in bipolar devices. And of course, these must not be confused with one another. Okay, so then what happens? Well, as the VDS drops, as this voltage comes down, at some point, this ID begins to drop. And that edge is equal to VGS minus VTH. So remember, this VGS has to be greater than a VTH. So there's an overdrive, so to speak. There's a margin between these two. That margin is called the overdrive voltage. And if the drain source voltage comes below the overdrive, then the device comes out of saturation. And this region is called the triode region. Some people call it the linear region. So for amplification purposes, we prefer to operate here. There are some other MOS circuits that also operate here, but those will not be covered in 115B. Okay, so we would like to find the equation for the current in these different regions of operation. So we say in saturation, this is what we have. ID is equal to 1/2 mu n C ox W over L VGS minus VTH squared. Mu n is the mobility of electrons inside the channel. So we have some number for that. C ox is the oxide capacitance between here and here per unit area. We have some number for that. We are given that number. W is the width of the device. That's the dimension into the page. And L is the length of the device from here to here. So that's L. Okay? And VGS minus VTH is the difference between what we have applied here and the threshold of the device. So again, That's something we call this the overdrive. All right, so with this equation, we can find how much current flows through the device, this current, if we are in saturation, meaning if VDS is large enough. All right? Okay. Now, you might recall that the MOSFET has one imperfection, and that has to do with the fact that in this area, in this region, as the drain source voltage increases, this equation says that the current must be constant. But in reality, it's not. In reality, there's a pinch-off point here that pushes back towards the source, and the channel begins to shorten. And when that happens, you can imagine if L becomes a function of VDS, then the current becomes a function of VDS. So how do we model that? Again, we resort to a very simple model, first-order linear model. And we say, okay, let's just multiply this by something that has VDS in it, so that when VDS goes up, the current goes up. All right? And again, we have to make sure the dimensions are right and everything else. So we're going to multiply this by a factor which we call lambda. That's called the channel length modulation factor. And then we're going to add 1 plus 2 here. So if we say channel length modulation is neglected, this term goes away. And we have a completely flat line here, so it's an ideal current source. But if channel length modulation is included, then we have this term as well. So in saturation, this is called the large signal model. Large signal model. And again, it simply emphasizes that VGS and VDS and ID can vary all over the place. As long as we are in saturation, as long as the device is on, this equation is valid. Okay, that's what we mean by large signal behavior, large signal operation. Okay, so again, in analogy with a bipolar device, we can visualize this transistor and see whether it's in saturation or triode. So for visualization, let's change the color. So say visualization. I didn't bother to write the current in the triode region because we will not need it in 115B, but of course there's another equation, if you remember, for the triode region. Okay, so here's how it goes. If we have some voltage like this, if the drain is high enough, then the device is definitely in saturation, meaning we are here. If these two become equal, the device is still in saturation, right? Because for the device to be in saturation, we need the following, right? So this region is defined as VDS is greater than VGS minus VTH. So all that means is that we should be looking at the drain and the gate. We don't even need to worry about the source. If the drain is below the gate by more than a threshold, the device is in the triode region. So that would be way over here. If the drain is below the gate by more than a threshold, then we are in the triode region. So obviously this is far from that, so this is still in saturation. To bring the device to the edge of saturation and triode, VDS must be equal to VGS minus VTH. So this voltage is equal to this voltage minus the threshold. So the way to think about it is that the gate has come up or the drain has come down to the point where this difference is one threshold. And this is at the edge of saturation and triode. All right, so it's important to remember this visualization, or you can always just go back to this equation and see if it holds or not. All right, So let's go on and construct the small signal model of the transistor. So small signal model. So the development is very similar to what we did for the bipolar device. We have a dependent current source, a GM VGS. This is VGS. Actually, in our models, typically we call that V1. So let me be consistent here. Call that V1, and this is V1. This is our gate. This is our source. This is our drain. All right, GM has the same definition as before. So GM indicates how strong this device is. If I change this by delta V, how much current change do I get in the drain? So GM is defined as the change in ID with respect to change in VGS. All right, so this is the simple small signal model of the MOS transistor. And again, I emphasize this model is valid for NMOS and PMOS devices. There's no distinction. So also valid for PMOS. All right, so we got that. But remember that if I go with this model, just like the bipolar case, it says that the current drawn from the drain is only a function of what's happening between the gate and the source. It knows nothing about what's happening between the drain and the source. And we said that's not true, because if this voltage goes up and down because of channel length modulation, because of this factor, the current actually changes. So somehow that has to be reflected in the small signal model as well. So for that, we put a resistor here, and that resistor models the channel length modulation of the transistor. Okay, so just like bipolar device where GM was expressed as the bias current divided by VT, here we have some equations for GM. So we're going to write 3 equations for GM of a MOSFET. So one is mu n Cox W over L VGS minus VTH. The other is 2ID over VGS minus VTH. And the third one is root 2 mu n Cox W over L ID. All these 3 equations are useful, and they depend on what we're trying to do. So sometimes we use this one, for example, if VGS is changing. Sometimes we use this one, for example, if ID is changing, etc. So depending on what we are keeping constant, what we are changing, one of these might be useful. And these are all bias quantities. So VGS is the bias quantity. ID is also the bias quantity. We also have an equation for RO. RO is simply given by lambda over ID. Lambda is given for a given transistor structure, and ID is the bias current of the device, so we can also find RO. Okay, so now that we have all of these, we can go ahead and build some MOS amplifiers. Let's see if there's anything else that I wanted to mention. Okay, one interesting point is that unlike the small signal model of the bipolar device, we do not have a resistance between here and here. There's no such thing as R pi for a MOS model. Why is that? Well, the difference is that in the case of bipolar device, we have a base current, and when the collector current changes, the base current has to change, because one is beta times the other. Whereas in the case of a gate of a MOSFET, remember that this is an insulating piece of material, so at least at low frequencies, there's no current going this way. So at low frequencies, It looks like an open circuit, and that's why we have an open circuit here. Okay, so let's go on to MOS amplifiers. And the development here is very much similar to bipolar amplifiers. So we have similar stages. So we have a common source stage, a common gate stage, and a source follower, just like the emitter follower. So source follower. Okay, it's almost as if you just went to every bipolar amplifier circuit and took the bipolar device out and replaced it by a MOS device, right? It's very similar, but of course the small signal models are a little different, right? There's no RPi here. Okay, so we start with the CS stage. And here's how it goes. The input goes to the gate of the device. The output comes out of the drain of the device. And we call this resistor RD, the drain resistor. We call this supply VDD, a drain. In the case of a bipolar circuit, we call it VCC, collector is VDD. Okay, so as usual, we want to find three parameters: the voltage gain of the circuit, the input impedance or resistance, and the output resistance or output impedance. Okay, so the voltage gain is exactly the same as what we found for the common emitter stage. So minus GM times RD. Well, the input resistance is how much? Looking into here, with this grounded, what do I see? I see an open circuit, so it's infinity, right? So it's infinity, but the key is that this is only true at low frequencies. In fact, in this course, sometime later, we will include the capacitances of these devices in the circuit, and then we will see that the input impedance is not infinite. All right, but for our purposes right now, for 115A purposes, the open looks like an open circuit, and the input looks like an open circuit, so it has an infinite impedance. And how about the output resistance? R out is equal to RD, and in these I have assumed that lambda is equal to 0. All right, so lambda here is similar to the early effect in the bipolar model. Okay, so long as you remember the similarities between the bipolar amplifiers and MOS amplifiers, it's much easier to keep track of everything that's going on. Okay, now with that, we are ready to look at our next problem. But let me try to make things a little more interesting. So all the blue writing here corresponds to the case of lambda equals 0. So I'm going to switch to red and say lambda is not 0. And I would like to see what happens here. It should be easy, right? Okay, so all that happens that in the small signal model, there's an RO to go into ground. So I have taken this out of the model and explicitly drawn it here. So then what happens? The voltage gain is given by minus GM times the total resistance seen between the drain and AC ground. RD going to AC ground, RO going to AC ground. They are in parallel. So I just do this. Okay. The input resistance, that doesn't change. It's still an open. The output resistance. We sit here and look this way. What do we see? We see RO to AC ground, RD to AC ground. So these go in parallel. Okay, so you can see that including the effect of channel X modulation is pretty quick in this simple case. Okay, let's go to our next problem, which capitalizes on this idea here We are on page, no, we should go to page 5. Okay, so this is problem number 5. Let's see. So we have the following circuit. We have two circuits we want to analyze. So here's a PMOS device. Here's an NMOS device. V in going in, V out coming out. And the PMOS device, so call this M1, call this M2. The PMOS device needs some sort of bias voltage here, VB, so that it's turned on, it acts in saturation and everything, all the good stuff. So in these circuits that I have shown you so far, I have not included all the bias circuitry necessary. Remember that the first step is always to create the right bias conditions. I haven't shown you all the bias circuitry. I've shown just the core of the circuit and its behavior with respect to signals that are coming to the circuit. Okay, so we have this circuit, and we'd like to find AV and R out. The input impedance is infinite anyway, so we don't worry about that too much. And then we call this part A. And for part B, we have the same topology. So M2 here, M1 here. And this time we have a bias voltage here, and our input goes here. And our output is the same here. So I can add a little note just to make things a little clearer for you. So in this case, M2 is acting as a current source. Okay? So it's just bias, it's acting current source in saturation. And then this device is acting as an amplifying device. And by the way, we're assuming that all these devices are in saturation. Whereas in this case, M1 is acting as a current source, nominally constant current source. And M2 is acting as an amplifying device because the signal goes to its gate and comes out of its drain. So again, we want to find, for part B, want to find AV and R out. Okay, assume all transistors are in saturation. And of course, in this case, we cannot assume that channel length modulation is neglected, as you will see. Okay, so this brings us to the next MOS amplifier, which is the common gate stage. Just like the common base stage in bipolar technology. So VDD here, RD here. The input goes to the source, and the output comes out of the drain. All right. Okay, so how about the voltage gain? And again, we assume that lambda is 0. The voltage gain, we go back to the common base stage. We saw that the voltage gain was Gm times this resistance with a positive sign. So the same thing here. So it's Gm times this resistance. The input resistance is low. Looking into here, we see 1 over Gm, just like the bipolar counterpart. So this is 1 over Gm, 1 over Gm. And the output resistance, if you sit here and look, we see RD to AC ground. Looking down, we don't see anything because lambda is 0. The output resistance of the device is infinite. So R out is just RD. Okay, so that's a simple common gate stage with its parameters. All right, let's talk about the third MOS amplifier stage, the source follower. So just like the bipolar circuit, we have something like this. The input goes to the gate, the output comes out of the source. Now, in the ideal case, we can neglect channel X modulation, and we can put an ideal current source here. In that case, the gain would be 1. But let's make it realistic. So let's put a resistor here and call that RS. Okay. So how much is the voltage gain in this case? So again, just like the bipolar counterpart, the emitter follower, we say this resistor divided by that resistor plus 1 over Gm. The input resistance is still infinite, so don't worry about that. The output resistance is given by this resistance in parallel with 1 over Gm. So Rs in parallel with 1 over Gm. All right. So once you have a catalog of all these equations, then it's easy to look at a more complex circuit and try to identify these basic building blocks and identify their parameters, their gains and input and output impedances, etc. And then we can have a better understanding of the more complex circuit. Okay, so that's the source follower. And that brings us to problem number 8. Let's see. Problem number 5. Okay, I'm trying to make sure I'm going in the right order. So this would be, let's go back to previous page to make sure we are keeping track of, okay, so that's problem number 5. This will be problem number 6. Problem number 6, we want to analyze the following circuit. Okay, am I missing, okay, maybe I'm missing a problem here. Let's just make sure that the numbers are correct. So here we had, let's see, problem number, the last problem we had on page 3 was, let's see, problem number 5 here. Okay, so this problem number 5, yes, I have to make a correction. Go to page number 4. Okay, page number 4 does not have a problem. Then we go to page number 5. So this is problem number 6. Please make this correction. This is problem number 6, not number 5. And then this will be problem number 7. Problem number 7. And here's the circuit we want to analyze. V in goes here. This is M1. And then what we have is, looks like this. Okay. The following. So we have an ideal current source here. And then we have a transistor like this, M2, whose gate goes to a constant bias, and the output is taken here. And you can assume that lambda is not 0, so we do need to include channel length modulation in the circuit. Okay? So you can see that M1 is still acting as a source follower because the signal goes to its gate and comes out of its drain. It comes out of its source, right? This is a source follower. Except that we played a trick and we have attached this M2 there just to be annoying, right? We want to find the voltage gain from V in to V out and the output resistance. So AV and R out. Okay, that's problem number 7. All right, so these are the basic amplifier topologies in MOS processes, and they're very similar to their bipolar counterpart. So we have to just keep all these equations clear in our heads so that we can do these calculations. All right, there's one more note that I would like to make so that we keep that also in our library of devices, and that's what we call a diode connected device. This applies to both bipolar and MOS transistors, but we just look at it in MOS technology because that happens more often in MOS technology. And it looks like this. We have a transistor, NMOS or PMOS, and we connect this gate to its drain. So now this looks like a two-terminal device because there are only two wires going to this transistor. There's a fourth terminal from MOSFETs, namely the substrate or body, but we have not talked about that in 115A, and we will not talk about it in 115B. But in graduate courses, we do include the body effect. Okay, so here we have only two terminals. And that means that this should be equivalent to a two-terminal device that we know from Circuits 101. For small